So we started with phase and frequency measurement in the last session, and we'll be starting with phase measurements first. So we can measure phase using different devices. One of the simplest methods of measuring phase is by measuring power factor, and once we have the value of the power factor, we'll be able to derive the phase from the power factor itself. So there are other methods of deriving or measuring phase. You have synchronoscopes for measurement of phase. You have phase sequence indicators, extra. So there are other devices that can be used for phase measurement. We'll be taking up power factor measurement device for measurement of phase. So in terms of power factor measurement, there are two methods. There are two types of power factor measurement devices. First of all, power factor meters. We can measure power factor using two methods. Either it can be an indirect method of measurement of power factor, or there can be a direct method of measurement of power factor. So in indirect measurement method, what we can do is we can measure the values of power, we can measure the values of voltage, we can measure the values of current, and using mathematical equations we can say what is the value of power factor. So this is one method of calculating power factor or measuring power factor. Now this method is inaccurate because we are actually using three different measurement devices to measure power, voltage and current. So the accuracy definitely is lesser in such a case as compared to a case where you will have that direct measurement of power factor. So this is one method, the indirect method. The second method will be the direct method of measurement of power factor. So I will not be explaining this slide. So there are two types of power factor devices. One is the electrodynamometer type, and second one is the moving iron type. In general case, the power factor device looks somewhat, be it the electrodynamometer type or be it a moving iron type, both the structures look somewhat similar to that of a wattmeter. So you can measure power factor indirectly or you can measure power factor directly. Once you have power factor, you can say what is the value of phase. So we are actually measuring the phase. We are actually dealing with phase measurement. So phase measurement can be done through measurement of power factor. Now as far as power factor goes, we can measure it directly or indirectly. Indirect method means you measure voltage, you measure current, you measure power, and from those values you derive the value of power factor. That is the indirect measurement technique. That is inaccurate because you have three different measurement devices. You have all the three devices will have their own errors, so you will have a combined error once you calculate power factor. On the other hand, you have the direct measurement. That means you have only one device that will give you directly the value of the power factor. So it will only be having it will be only accumulating errors of one particular device. So definitely the power factor direct measurement of power factor is much more accurate as compared to the indirect measurement method. Now as far as power factor devices go, there are of two types, the electrodynamometer type or the moving iron type. Both these two structures, their configuration, their construction is somewhat similar to that of a wattmeter. Similar in the sense that both of these two devices have current coils and voltage coils. Voltage coils, potential coils, or pressure coils, whatever you want to call it, voltage coils, pressure coils or potential coils. So they will have current coils and potential coils. So in the last session we started with the electrodynamometer type. So again, in the electrodynamometer type you have the single phase type and you have the three phase type. Now in all of these structures there will be a current coil and a pressure coil. So in the single phase electrodynamometer type, you have a current coil that's fixed, and you have a voltage coil. Fine. So this current coil is fixed here, while as the voltage coils, they are moving in nature. They will not be fixed coils. They will be moving in nature. That means they are actually rectangular bars here, as you can see, and using some arrangements, brush extra, they are connected to fixed coils. So in electrodynamometer type single phase, you have the current coil that's fixed, while as you have the voltage coil that is moving in nature. Right? Now this moving voltage coil is further divided into two parallel paths. One of the parallel paths, that's A, is connected with a series resistance R, and another path B is connected with a series inductance L. That means the voltage coil in case of electrodynamometer type is divided into two parallel paths. One parallel path is resistive in nature, another parallel path is highly inductive in nature. Both these two voltage coils, they are proportional to the applied voltage, that is V in. Right? So the current will flow in the system. So the main current that is flowing in the system will flow through the current coil. Fine. While as the voltage proportional current will flow through the voltage coils. As far as the current is concerned in coil A, in coil A what will happen is that the current will be in phase with the applied voltage because it is resistive, while as in the parallel path B of the voltage coil, as it is inductive, the current will be lagging behind the applied voltage, and since it is highly inductive, it will be almost lagging behind by 90 degrees. Fine. So you have the voltage coils A and B. One is resistive, purely resistive, another one is purely inductive, say. So the currents in the two parallel paths of the voltage coils will be lagging behind each other by 90 degrees. So what we do is that we also mechanically place these two bars, that's coil A and coil B, at 90 degrees to each other. Now the current flowing in A and B, they are having a phase difference of 90 degrees, as well as mechanically the two coils A and B, they are placed 90 degrees to each other. You now know that once we apply the voltage, current is flowing through the main coil, that's the current coil. It will produce its own magnetic field. Current is also flowing through A and B, both coils. They will produce their own magnetic field. Because of the interaction of the two magnetic fields, torque will be induced on the coils A and B, since they are rotating in nature. So both coils A and B, a torque will be induced, or you can say a deflecting torque will be induced on coils A and B. Now this deflecting torque A and B, that will be applied to A and B. Torque that will be applied to coil A will be proportional to the current flowing through the main coil, as well as current flowing through the, if I only talk about without going into the actual formula, torque induced on coil A will be proportional to the main current will be proportional to the current flowing through the current coil, as well as proportional to the current flowing through coil A. So in other words, since current flowing through coil from the main coil is it will be proportional to cos phi, and current flowing through the coil A will be proportional to sin theta. So in other words, your induced torque on coil A will be proportional to cos phi sin theta. Right? You have two voltage coils. They are divided into, you have a voltage coil divided into two parallel paths. One parallel path is purely resistive, another parallel path is purely inductive. So current in the two coils will be having an electrical angle of 90 degrees. We also place these two coils mechanically to each other at 90 degrees. Now the current is flowing through the current coil as well as the pressure coil. So it's AC current flowing through these. So a magnetic field will be produced. Because of the interaction of the two magnetic fields, a torque will be induced on the coils A and B. These are both pressure coils. Coils A, coil B, they are both pressure coils. Now they are located 90 degrees to each other, as well as their current flowing through them is electrically having a phase difference of 90 degrees. So torque induced in A will be proportional to cos phi sin theta, while as torque that will be induced in B that will be proportional to cos of phi minus 90 degrees. It is electrically 90 degrees lagging, as well as it is mechanically lagging by 90 degrees. Fine. So your torque will be induced on both coil A as well as on coil B. In case of coil B, the current is lagging by 90 degrees, as well as it is mechanically located 90 degrees from coil A. So what happens is, once the torque is applied on both these two coils A as well as coil B, there will be some deflection, but after some time, after some rotation, torque A as well as torque B will balance out each other, and net torque will again be equal to 0. So at that condition, when tau in A and both the deflecting torques will cancel out each other, there will be no more rotation, they will come to standstill. You can equate the two formulas. You will find that cos phi sin theta will be equal to you'll see that it will be equal to cos theta sin phi. This was actually here sine of theta minus 90 degrees, cos of phi minus 90 degrees. We know cos of phi minus 90 degrees is sin phi, and sine of theta minus 90 degrees is cos theta. So in other words, cos phi sin theta will be equal to cos theta sin phi, or in other words you can simply say that phi will be equal to theta. So once the two deflecting torques are equal, the net torque induced on the pressure coil becomes 0. At that time, phi will be equal to theta. That means the electrical difference, the electrical phase angle between currents will now be equal to the mechanical deflection that will be noted from the indicator that's attached with the coil B. Here, going back to the structure, you can see there is a indicator that's actually attached to coil B. Fine. Principle ये है कि there is a pressure coil that's divided into two segments. One is purely resistive, another one is purely inductive, and you also have a current coil. So taking one by one, current coil and coil A, they are both carrying currents. They will produce their own magnetic field. One coil A is movable, so when torque will be induced on coil A, it will start rotating. Coil B is also carrying current, but the difference is that coil B is carrying a current that is lagging behind the current in coil A by 90 degrees, as well as it is mechanically located to coil A at 90 degrees. So that torque that will be induced, the interaction between the fixed coil, that is the current coil, and coil B will be such that the torque will be equal, but it will be anti-clockwise in nature. So both these two deflecting torques on coil A, coil B will eventually subtract out each other, will balance out each other. The net torque induced on coil A and coil B will be equal to 0. So at that particular time, you will see that phi will be equal to theta, as the phase difference will be equal to the mechanical degree, mechanical angle that is between A and B, that is matching actually with the plane of reference. So this was a case of single phase electrodynamometer type. In case of three phase, Now you have understood the principle that you need to actually make sure that the currents in the two pressure coils are not in same phase. So you introduced an inductance in case of single phase electrodynamometer type, but in case of three phase electrodynamometer type you do not need to introduce inductance. Again, you have a current coil here that's fixed, as well as far as the pressure coil goes. In case of a three phase, what you do is one coil, say for example coil segment 1 here, it will be connected between phase A and phase B. Another coil, that is coil 2 here of the pressure coil, that will be connected between phase A and phase C. Now you do not need to introduce an inductance here because there is already a natural phase angle between VAB and VAC. VAB is the voltage here applied to coil 1 and VAC is the voltage here applied to coil 2. So VAB and VAC, they are having a certain phase difference between them. So that means the current flowing through these two paths will also have a same phase difference if they are purely resistive. Fine. We are only introducing resistances here. So in case of three-phase electrodynamometer type, you do not need to introduce an inductance that is natural to a three-phase system. You have a certain phase difference between VAB and VAC. Now accordingly, that phase difference will be 60 degrees. So you need to make sure that these two coils, in this case coil 1 and coil 2, they are also located mechanically to each other at 60 degrees, not at 90 degrees now. In case of single phase electrodynamometer type, since we are using an inductor, purely inductive, it was almost 90 degrees. So we were also keeping a mechanical 90 degrees between them. Here VAB and VAC, they will have a phase difference, but that will not be 90 degrees, somewhere around 60 degrees. So we are keeping the mechanical angle between VAB and VAC again 60 degrees. Then the same principle will occur. Current IA is flowing through the current coil. Current IAB is flowing through coil 1. Current IAC is flowing through coil 2. They will have an electrical phase difference as well as a mechanical phase difference. So balancing out each other, calculating the torque that's actually given here, cos of 30 plus phi sine of 60 plus theta, and torque 2 cos of 30 minus phi sine of 120 plus theta. At balanced condition, and both these two torques cancel out each other, torque 1 will be equal to tau 2 at that particular time, and tau 1 is equal to tau 2. This condition will be met. That means phi will be equal to theta. So this is actually the principle of an electrodynamometer type. You divide the pressure coil into two segments. They will be carrying currents that will have a phase difference, the same mechanically the same phase different. While construction, we keep the same phase difference between the coils A and coils B. So I hope this is clear. This was about the electrodynamometer type. If there are any more questions, we can ask in the group. Today we are taking up the second type, that is the moving iron type. The principle is same, that is the construction is similar to that of a wattmeter. In other words, the moving iron type will also have a current coil and a pressure coil. So you have the moving iron type. Now this is again divided into two types. The moving iron type is one, it is the rotating field type. Rotating field power factor measurement device, and So you have two types of moving iron instruments, moving iron power factor instruments. One is the rotating magnetic type, that's actually working on the principle of rotating. That means actually a rotating magnetic field will be generated in such a type, while as in case of alternating field type, you will have alternating field. We'll see to that.
सर आपकी आवाज कट रही
ज़्यादा कट रही है. You have the rotating field power factor measurement device and the alternating field power factor measurement device. So starting with the rotating field type. So this is how a rotating field type looks like. Construction wise, it has three coils, three fixed coils, A1, A2 and A3. These are actually current coils. Fine, so you can see actually A1, A2 and A3. These three coils, they are fixed and they are actually the current coils. So they will be carrying, this is now a three-phase system first. So they are connected to three phases, 1, 2 and 3, or ABC, whatever you want to refer. So this is your supply side, and this on this side there will be the load. In between the power factor measurement device is connected. So there are three current coils, A1, A2 and A3, fixed with the three lines 1, 2 and 3. And besides that, you have the pressure coil or the potential coil, whatever you want to call it. Coil P is the pressure coil here. This is the top view of this coil. Now this pressure coil, along with, it's also fixed. It consists of a cylinder in between. Fine. So this is your pressure coil here. This is your coil P. It will consist of a cylinder in between. On either side of the cylinder there are guiding vanes. Fine. So you have the vane on either side of these two cylinders, and attached with this vane is also the pointer that will actually show the reading, as well as damping vanes. So one thing you need to make note of, in electrodynamometer type instruments, in electrodynamometer type power factor instrument, we do not have any controlling mechanism. We do not need damping circuitry. We do not need any control circuitry to damp out the oscillations. But in case of moving iron instruments, there will be a control circuitry. There will be damping introduced. We need to have a damping torque as well to damp out the oscillations. So you have two different coils. You have A1, A2 and A3 attached to three phases, representing the pressure coils representing the current coils, and you have the coil P that's placed in the center of these three coils. It's also fixed. Coil P is fixed. Fine. It will be the pressure coil, but in between this coil P there is located an iron cylinder. That's why the name iron. That will be actually rotating this iron cylinder, and on either side of this iron cylinder there are vanes, guiding vanes, on which actually the torque will be applied. And also attached with this structure, also attached with this cylinder, is the pointer that will give us the readings, and you also have the control circuitry to damp out the oscillations. to produce the control or damping torques. This thing was absent in electrodynamometer types. We do not need any control mechanism in electrodynamometer types. They are self-controlling. So now the principle is somewhat similar to that of electrodynamometer type. You have A1, A2 and A3 attached to 3 lines. So they will be carrying currents I1, I2 and I3, the 3 line currents. So they will produce their own magnetic field, as well as coil P. Coil P, as you can see, it's attached to any 2 phases. In this case, it's attached to phase 2 and phase 3. This coil P is attached to phase 2 and phase 3. So the voltage that will be applied to coil P will be V23. Fine. The line voltage V23 will be applied to the pressure coil. And this current, it will be carrying a highly resistive This pressure coil is attached to lines 2 and 3 of the 3-phase circuitry with a series resistance a very high series resistance. Fine. We want to actually make sure that the current flowing through this coil P, IP, is almost in phase with the voltage V23 that will be applied to this coil. So V23 is applied to coil P, so it's carrying current IP, so it will be producing its own magnetic field. The current coils A1, A2, A3, they are carrying the line current simply I1, I2 and I3. They will be producing their own magnetic fields. So the interaction of the 2 magnetic fields will actually cause a deflecting torque, and this deflecting torque will be applied to the vanes of this vanes that will be actually the moving part in this case, that are attached to the cylinder. So you'll be having torque being applied to the upper vane as well as torque being applied to the lower vane. So let's first of all see the phasor diagram of this. V23, I am taking V23 as the reference. It's actually the line voltage that's applied to the pressure coil. So you'll have V12 at 120 degrees, you'll have V23 and you will have V31. Accordingly, you can say the phase voltage V1 will be at 30 degrees to V12, V3 will be at 30 degrees to V31, and V2 will be at 30 degrees to V23. Then you have the line currents I1, I2 and I3. So I1 and V1 will have a certain phase difference. That's actually what we want to measure. So I took V23 as a reference. V12 will be 122 V23, V31 will be 122 V23. Fine. And you'll have the phase voltage V1, V2 and V3 at 30 degrees. So this will be almost an angle of 30 degrees. And I1, I2, I3, the 3 line currents, depending upon the load, whatever is the load, whether it's inductive, resistive, whatever is the load, you will have phi, the phase difference between the line currents or the phase currents and the phase voltage. Now as far as IP goes, this will be IP, the current flowing through the pressure coil. As I said to you, V23 is the voltage that is being applied to the pressure coil, and we are connecting it through a we are connecting it through a we are having a series resistance attached to it that's of a very high magnitude. That means IP will be nearly in series in phase with V23. IP is almost in phase with respect to V23. So this is the phasor diagram. The principle is A1, A2, A3, they are the current coils. They are carrying currents I1, I2, I3. These are AC currents, so they will be producing their own magnetic field. V23 is the voltage that is being applied to coil P. It's stationary in this case. It will not be moving, the coil itself. But the cylinder that's attached in between this coil P, it is carrying the vanes extra. So that will be rotating here. So coil P will be producing its own magnetic field. A1, A2, A3, they will be producing their own magnetic field. The torque will be induced on the vanes. So both the vanes will experience deflecting torque, and once there is a balance, once the deflecting torques balance out each other, we can measure the value of the phase difference. So in this case, the deflecting torque from the phasor diagram, you can say it will be proportional to, this is not the exact value, it will be proportional to I1 IP cos of 90 minus phi sine of 90 plus theta. These are the deflecting torques on the vanes of this cylinder, where theta is this angle. It is the angle that the vane will
सर IP का फेजर कैसे बनाया आपने?
IP V23 is the voltage that is applied to the pressure coil. Fine. And I am saying that it is connected through a very high resistance, very high series resistance. Actually, the load will affect the phase between IP and V23. But since I am saying that is connected through a very high value of resistance, that means IP will be almost in phase with respect to V23. ठीक है?
ठीक है सर.
It's almost in phase with respect to V23. It's almost parallel with to V23.
Okay sir, thank you.
Theta is the angle that the vanes will form in this case with respect to the line of reference. You can take any plane of reference and you can see what is the value of theta. So the torque, the deflecting torque on the vanes will be proportional to, not equal to, I1 IP, that the two currents flowing through two different coil segments, and the phase difference that they will be carrying, cos of 90 minus phi sine of 90 plus theta, plus I2 IP cos of 330 minus phi sine of 332 plus theta. So this is your total deflecting torque that will be proportional to the individual currents flowing through three different coils, as well as the current flowing through the pressure coil, the interaction of the currents through the different coils and the pressure coil. So at standstill, or once the balance is met, once there is no more deflection, at steady state condition, tau d will be equal to 0. Fine. At steady state condition, tau d, the deflecting torque, will be equal to 0. The net deflecting torque will be equal to 0. As well as for a balanced three-phase circuit, for a balanced three-phase circuit, I1 it will be equal to I2 will be equal to I3. That means once I1 equal to I2 equal to I3 and tau d, this whole equation is equal to 0, you can say cos of 90 minus phi sine of 90 plus theta plus cos of 330 minus phi cos of 90 minus phi sine of 90 plus theta plus cos of 330 minus phi sine of 210 minus theta plus cos of 210 minus phi sine of 330 plus theta. This will be equal to 0. So this equation is equal to 0. So once you solve this equation, you will see that this equation is true for phi equal to theta. So whatever the deflection of the vanes from the reference axis, and that will be actually the measure of the phase angle between the line currents and their corresponding phase voltage. ठीक है, जो I1 और V1 के बीच में phase difference था, that's phi, that can be measured from the deflection of the iron vanes. That iron vein is now connected to a pointer, and that deflection will show us the readings. In this case, you have to note that the three current coils will produce a rotating magnetic field similar to that of an induction motor. So that means what it will actually do is it will try to drag the system forever. It will try to drag the system for as long as it can run. Right? So to make sure that the drag is actually nullified, we are using damping vanes in here. They will be in opposite directions, so they will cause a rotation in the opposite direction, and that will cause the system back to standstill. That will actually make sure the speed of this rotation is actually damped out. Okay, so the principle is that of is simple. You have current coils and a moving coil. Here the current coils, there are 3 current coils and 1 pressure coil, and the 3 current coils will produce a rotating magnetic field that will actually cause the rotation of the vanes connected to the iron cylinder. So in order to make sure that the rotating magnetic field does not keep on dragging this cylinder forever or for a longer period of time, we make sure there are damping vanes that will produce an opposite damping torque to reduce the speed, as well as what we can do is we can use a very high resistive iron cylinder.
सर बट सर वेट कर रहे हैं उनकी क्लास, अब उनने फ्राइडे को 11 बजे रखी है, हमारी एमसीएस कंप्लीट हो गई ना, तो नमाज से पहले ही लेंगे क्लास.
ठीक है, तो दिस इज ऑल फॉर टुडे, देन वी विल कंटिन्यू इन द नेक्स्ट सेशन.
थैंक यू सर. अस्सलाम वालेकुम.
वालेकुम सलाम.